a presentar brevemente a Miles. Llevo hablando con Miles 2 años para este día. Él es profesor en el grado de Computing Education en una universidad de Reino Unido. Pero lo más importante para el día de hoy es que es uno de los padres del modelo de enseñanza de Computer Science, que a mi juicio es uno de los referentes, o al menos en el que yo más me he inspirado, el modelo británico. Él contribuyó a crear un nuevo currículum, pero os va a hablar que no solo es importante el currículum, sino la formación al profesorado y, digamos, lo que invierte el gobierno para que ese currículum y esa formación pueda llevarse luego a las aulas. Es padre de muchos modelos de currículums, tanto primaria como secundaria, los modelos formativos y un montón de programas para divulgar el arte de las ciencias de la computación. Así que, sin más, Miles, you are ready?
I am. Thank you very much. Cristian, thank you so much for that introduction and for the invitation to be here. It is such a pleasure to join you for this conference. It really is. And so nice to be able to do that in person rather than via Zoom, which is what we thought we were going to have to do. What I want to do with my 40 minutes or so is tell you the story of the last, I don't know, about 12 years or so of the journey we've gone through of putting, thank you, gracias, of putting computing onto England's curriculum as an entitlement for all of our pupils. So, something of the story there. Okay, first slide. There we go. Right. So back in 2010, change of government from the old Labour government, a socialist government, to a coalition government made up of the centre-right and right parties, the Liberal Democrats and the Conservatives. Before that, folks were going abroad and seeing what high-performing jurisdictions were doing in terms of their national curricula. One of those people was Tim Oates, and he wrote this very influential paper, looked at education in these high-performing jurisdictions and saw that they had adopted a coherent approach of 6 elements to their curriculum design, of content, of assessment, of pedagogy, the teaching strategies, of training for teachers, both initial teacher training and professional development, of teaching materials, the textbooks, the publications, as well as the incentives, the measures that were in use. And this, I think, formed a big part of the new government's thinking about how to do curriculum change. That said, this right-wing government decided to step back from the detail of implementation. They said that government should only do what only government can do, which is very much a small government perspective. So that's the initial setup for this. 7 years on, 2017, it turns out that this was not the best way to do it. That by taking this small government, doing very little other than setting the standards approach, the best that we could describe the situation as was patchy and fragile. That we had islands of good practice, but without doing this at scale, we didn't really know that we were doing it particularly well. Yes, it was working well in some parts, but you needed some level of intervention there to ensure that this was stable and would continue into the future. So come the budget of 2017, then we get central government funding to do this properly, of 80 million or so being set aside to establish proper training for computing teachers, a network of support, ensuring that there were enough new teachers to teach this subject up to GCSE standard, that there was a support system in place for those doing the 18 plus, the difficult qualification in computer science. And yes, we started to think through how to get something approaching a better gender balance in this subject, girls remaining a minority. So that's the overall story. I'm going to focus in on the details, and I'll use those 6 things from Tim Oates' idea of content and assessment and pedagogy and all of the rest as a structure for this talk. So let's start then with the content. As I say, new government taking office in 2010 who decide to rewrite the whole of the school curriculum themselves. And they want to bring curriculum back to a very basic model of traditional academic subject disciplines of a knowledge-based, a fact-based curriculum. None of the sort of integration of IT across the curriculum and the notion of 21st century skills. That wasn't what this new government wanted to do. They wanted to bring it back to the basics, back to a knowledge-based curriculum of traditional subject disciplines. Thus, we have computing as a subject in its own right in our curriculum, rather than attempting to embed that in mathematics and other subject areas, for good or possibly ill. In order to draw up that content list, what we want to teach, the government again stepped back from implementation, asked the British Computer Society and the Royal Academy of Engineering to assemble a group of experts around a table to decide what the content should be. That drew on the sector representative bodies, that drew on academic computer scientists, software engineers working out in industry, and significantly teachers and people involved in teacher training. It was my great honor to be part of that process there, of those who were meeting around the conference tables, drawing up the curriculum, although I certainly cannot claim to be one of Britain's greatest computer scientists. That's definitely not me that they're talking about. The curriculum starts with this really noble ambition that a high-quality computing education should enable pupils to understand and change the world. We don't really talk about saving the world, but perhaps that's on the agenda for later. So what we have there is, I think, a twofold thing of the computational thinking as a way of understanding the world, of giving our pupils an insight into the world around them, and computing education as a way of empowering them with some sort of digital creativity to make a positive difference to their world, understanding the world and changing the world. When we tried to draw up the programs of study, I think we had in our minds this sort of three-layer model of computer science, of information technology, and some sort of critical digital literacy. I characterize that as the foundations of computing, the theoretical computer science, software engineering, being able to write programs, information technology, the applications, being able to get useful things done with computers, still being able to make PowerPoint slides and make Excel spreadsheets and so on. That remains part of computing education for us, as well as the implications of this for us as individuals and for our society as a whole, that sort of critical digital literacy element to it. So that's there. It fits on 3 pages of A4 paper. The programs of study from age 5 up to age 16 is just 3 pages. A lot of the detail is left to schools and the sector to decide on the implementation of this. And keeping it to a minimum, I think, really helped teachers and schools to feel that this was their curriculum, that they could do this their way. But it also meant that a lot of the responsibility for how to implement that wasn't sort of being done by people with much expertise within the area. It's worth my saying that we, as well as the national curriculum for computing, we do have 2 qualifications there. So at the age of 16, many of our pupils, about 1 in 7, 14% or so, will choose to take what we call a GCSE in computing or in computer science. A very small minority then go on to do an A-level in computer science at age 18. So a curriculum for all, elective qualifications for some, and for a very small number at age 18. There is a sense of progression there, that we start by laying the foundations for computational thinking, right with our very, very youngest pupils, before they even start in formal education. They're trying ideas out, they're learning from their mistakes, they're persevering when things get difficult. They're not using computers for this, but adopting those attitudes, adopting those practices, lays a foundation for the computational thinking, which we hope will come later. And then a real sense of progression as that computational thinking becomes more and more detailed as pupils make their way up through education. You have a similar thing happening with programming alongside that computational thinking, with some of that happening for 5 to 7-year-olds right at the beginning of primary education, and of course much, much more happening later on, introducing text-based programming sometime between the age of 11 and 14, all of the programming being in a text-based language by the time they're taking exams in the subject at age 16 or age 18. So object-oriented programming, functional programming there for that elective qualification at age 18. So that's how it started, with that sort of threefold model of foundations, applications, and implications. Now that we have funding for this, our new National Centre for Computing Education has redrawn the map for this and have produced their own taxonomy, their own model of curriculum, drawing, yes, on the national curriculum requirements, as well as the 16 and 18 plus requirements, and what's happening elsewhere. And by producing their own map, they've then gone on to produce their own resources based on their model of the curriculum rather than the national curriculum itself. Their taxonomy includes those 10 things. I think it might be of interest to you to notice that computational thinking isn't on that list of 10 aspects of computing that get taught. It's there, it's hinted at within algorithms and of course within programming, but it doesn't get a separate heading on their approach to taxonomizing computing education. I think one of the lessons that we've learned is assessment really matters. When it comes to what happens in school, the tests that pupils are working towards seem to have far, far more say on what happens in the classroom than the curriculum which folks like me sitting around conference tables actually wrote. And we should have realized that at the time. Getting the assessment right mattered. So alongside the new curriculum, we stripped out the whole of the old assessment methodology that we had until 2010. All of that framework goes, and all we are left with is this one sentence for every stage of education, for every subject. Pupils should have learnt the things that they have been taught, to paraphrase this. It is, yes, stating the obvious there. At the end of each stage of education, we should assess whether pupils have learnt the things that they were supposed to have been taught in that key stage. The details of implementation left to the sector again. Reviewing, so we take the national curriculum content and break that down into individual granular statements, and you can assess, has a pupil learnt about repetition in programs? Has a pupil learnt about modularity or functions or variables? It's possible to do that by producing good questions or looking at project work. One of the review bodies said the best way to go about this is to produce banks of questions, not just for computing, but for all subjects in the curriculum. Produce a national item bank of really good questions that teachers can use, yes, to assess their pupils' learning, but also as a way of driving what happens in the classroom, having a good test to work towards. In terms of software engineering, this is very much like test-driven development. First, write your test, then you'll know whether your software is working or not. Other subjects have not really met this, but for computing, as a new subject on the curriculum, we rolled our sleeves up and got on with the work there and produced a national item bank. And as of a couple of days ago when I put the slides together, we now have 11,320 multiple choice questions, most of them written by teachers themselves for use with their pupils, but shared nationally with other teachers. I think this is a phenomenal body of work, and it's there for free. The idea is to guide formative assessment, not for end-of-stage assessment of what has been learnt, but for the within the lesson assessment of have pupils learnt the thing that I've just been talking about. There's an illustration of one of these on the board, and one of the best things about this, because we've adopted this multiple choice format, is really getting to grips with the misconceptions, creating distractors in such a way that really gets pupils to think about what is it I don't understand, or getting teachers to think about what my pupils might not understand about this. So a simple question which looks as though it's testing selection is actually about typecasting in Python, that Python assumes everything input is treated as a string. This is a common misconception there. And we have a similar thing going on at A-level. Now with the new National Centre work, we have a bank of questions there for assessing, helping pupils to study computer science for that 18-plus elective qualification, and getting into really quite, I think, tricky territory about their model, their mental schema for object-oriented programming there. In the early days, we also had projects alongside questions. And so for that 16+ qualification, some really lovely project ideas. Many of you may be playing Wordle or the Spanish version of Wordle. This is a very similar thing, using just numbers as the thing that you're trying to guess. And getting pupils by the age of 16 to implement that through the medium of code seems like a really nice idea to aim for at that sort of switch point in education. The problem was, or perhaps the opportunity was, that once you put the spec out there for your coursework, for your project, implement a program that does this, almost every 16-year-old in the country is going to go off onto Google and search for how do I implement this project idea. And even the ones who don't search for that might just post their solution onto GitHub so everybody else can see their solution too. Our exam boards, the awarding organizations, really didn't like this idea of collaboration happening in computing. We don't want that happening. So decided they had to stop this project-based assessment, remove that component, and just rely on paper-based exams for assessing a pupil's ability to program, which I still think is really problematic. And you know what's going to happen in schools which are really worried about exam scores. All of the programming education will become a pencil and paper exercise rather than that experience of actually writing code that works on a computer, which kind of matters. So it's left now to the exam boards to find a way to assess practical programming. And what they've gone with is, yes, pencil and paper, or in one case, an on-screen exam, as well as the head teacher, the principal of the school, signing to say pupils have had the opportunity to learn practical programming. It's left to the schools to decide what the opportunity may mean. So we have problems there. Up at A-level, the questions get, as you'd expect, harder still. For this 18+ qualification, we're introducing some functional programming there, so pupils should have had some experience of that. At 18+, the qualifications still have good project work, though. 20% of the final exam is based on an entirely independent programming project. It isn't make a particular program for a particular specification. It's find something interesting to do, show us what you can do, with suggestions like an application of artificial intelligence or making a computer game, lots of opportunity for object-oriented programming using published APIs in order to do that. So the A-level 18+ project work is still very, very good. I was in a school a couple of days ago seeing some really nice work being done for exactly that. Let me turn now to questions of how we should go about teaching computing, the pedagogy of the subject. I think fundamental to this is my little sort of three-term equation there of the idea of programming itself is a two-step process. First, think about how you want to solve the problem, the algorithm, the computational thinking, the design idea, and then implement that as code. And I think even now, we're managing to maintain that approach to programming education of the design, the ideas, and then the implementation phase. And this, of course, references Jeanette Wing's work. I think we're much more happy with the second definition, or the later definition, of how we go about solving problems with computers. It's not just the application of big CS ideas to real-life problems. For us, this is about finding a way to make the computer carry out those solutions. If you wish, computational thinking without computation is really just thinking, isn't it? So we're looking for implementation, using computers as part of that. I think we've already had this reference today of the computing at school model of computational thinking, of those concepts on the left of the slide there, things like logical reasoning and algorithms and abstraction. But I want to draw your attention to the approaches on the right-hand side of the playfulness, the tinkering, the willingness to experiment, and seeing this as close to science or engineering rather than just a dry theoretical domain, of making something, of fixing things when they go wrong, of keeping going when it gets hard, and yes, collaborating, although obviously not for the exam work. There's a lot of enthusiasm. Sorry, I shouldn't show the slide just before lunch, should I? There's a lot of enthusiasm in English schools for the unplugged approaches of learning about the idea of an algorithm through coming up with our recipe for pizza. But I think many of us are worried that it just stops at that, and children come up with really good algorithms for making cups of tea or making pizza, but never have the experience of thinking about how that would be implemented as code, how you would find an automatable way of doing that. I think one of the ways we're addressing this is this idea of the semantic wave, that we start with the big picture idea, the abstract notion of an algorithm as a sequence of steps, as a set of rules to get something done. We then give pupils a very concrete idea of that, a concrete way of thinking about that, as my recipe for making pizza or whatever, and then move back up to the abstract realm of what that means in terms of a more formal algorithm, in terms of an algorithm that could then be translated into the programming language of choice. When it comes to programming, most English primary schools are teaching Scratch. That carries on into lower secondary schools. So we give a strong foundation in being able to program a computer without worrying too much about syntax. And yes, Scratch has its faults, but it's such an accessible language, so many opportunities for pupils to learn independently, autonomously, join the Scratch community, make really fun, exciting projects. And then, of course, after they've made all of these fun, exciting projects as part of a community, we then teach them Python. So it's a much more sort of formal language where they have to master the syntax. Our hope is that they've mastered the big ideas in the block-based language, and then all that remains is mastering Python's particular syntactic conventions, remembering about the indentations, remembering about the colons. It is more complicated than that, but it seems a good way of supporting the transition there to block-based programming. There are other languages introduced later. A lot of schools are using C# at A-level. There are some schools using Java at A-level. For that little bit of functional programming, Haskell is still a common language in some sixth forms at any rate. So, but those two form the bulk of the programming that gets taught. Rather than sticking with sort of Pappett's approach to we learn through just making things to show to others, which has been around since the 1980s, I think teachers have come to value an approach which recognizes the importance of predicting what a program will do. Sue Sentence, Chief Learning Officer at Raspberry Pi, one of the various highly esteemed academics in the English computer science education research community, has her PRIM model here. If you start by predicting what a program will do, then run the program, check that your prediction was correct, investigate it, make some modifications. What would happen if we changed this line of code? Modify it to make a different program, and then, and in her model, only then move on to the make phase of returning to that sort of Pappett constructionist model of creating something from scratch, or indeed in Python. I think still most teachers of computing in school take a very pragmatic approach to this. Yes, there is a recognition of the role that computer science education research plays, but it's still a very young discipline, a very young subject in the curriculum. And I still find a great joy in teachers just figuring out for themselves how to teach this well and sharing those stories with one another through communities such as computing at school. With the National Centre, though, we've started to adopt a more research-led approach, and they've come up with a very handy guide to 12 pedagogic principles that underpins the resources, the curriculum materials that they've produced. And I think that's a very helpful way of helping teachers to start to engage with what we know is effective practice within computing education. I draw your attention to read and explore code first at the bottom of that second column there, the idea of looking at code, of reading code before you start writing code for yourself. But also, there on the left-hand column, create projects of making something, of doing something that you find personally interesting and engaging. My day job at the University of Roehampton is training the next generation of secondary computing teachers. It's a job I love very much, and initial teacher training has to play a really important role in getting computing established, but so does the professional development for those in the profession. It's an obvious fact that the quality of any education system cannot exceed the quality of its teachers. And if we're serious about getting high-quality computing education happening in every school, then we need a high-quality computing teacher in every school. It is, I think, the only way of doing this. So for a lot of the material we did right at the start with the new curriculum, when it was very much led by the sector, we said, let's not worry about pedagogy, let's not worry about teachers' IT skills, let's focus on that middle bit of my equation there, the computer science subject knowledge. Relatively few secondary computing teachers in England have a background in academic background in computer science. It's less than 40% have a degree in the subject that they're now expected to teach. At primary, of course, it's an even smaller number. So our first priority was to make sure teachers knew enough computer science to be able to go into the classroom and teach that confidently to their pupils. And so even before we had the new national curriculum, we'd drawn up what content teachers needed to know in computer science. It seems the wrong way around, but this was seen as such a priority of identifying the subject knowledge for the subject. And so have this sort of five-fold model there: algorithms, programming, data, computers, and social informatics, communication, and the internet, and came up with the list of the things that should be taught before a student starts on their teacher training course or within that professional development program for those already in the profession. Now that we have the new National Centre for Computing Education, we've seen a huge success. This has been the focus of much of that £80 million spend on computing education. So we have 4,000 courses being delivered, 17,000 participants, 6,000 secondary teachers who have enrolled on this program to qualify as a teacher of GCSE computer science. So doing very, very well in terms of that professional development. It's not all a top-down approach led by facilitators, trainers from the National Centre. We've reinvigorated our grassroots computing at school movement with 330 communities there, 26,000 professional development activities since the National Centre was established. That's just extraordinary number when you think about it. And again, so a number of teachers who've engaged with the coaching, 36 newly qualified coaches for other teachers within that computing at school community, and a certification program that sits alongside that. 11,000 primary school teachers who've now obtained the CAS certificate, 3,000 secondary school teachers enrolled in that certificate, and 1,100 of those certificates already awarded to secondary computing teachers. So again, a success. Teaching materials really do matter. Again, I referenced Tim Oates' work on this one from 2014, of saying high-quality textbooks really do matter in terms of non-expert teachers as well as expert teachers being able to deliver this subject well in school. And the Publishers Association and Educational Suppliers Association drawing up guidelines as to what a good computing textbook or scheme of work should look like. In the early days, the publishing industry really stepped up to the mark with producing very accessible schemes of work for non-specialist teachers. I was involved in the Switched On Computing scheme on the left of the slide there, which I was very proud of being translated into Spanish. The Spanish translation not by me, I should emphasize. The National Centre has done that their own way. So they have this lovely sort of linear journey through the computing curriculum there, of a very, very clear model of progression. There's no requirement on schools to teach it this way, to follow this scheme of work, but it's been paid for out of taxes. It's given to the country, it's given to the world for free. And as I say to my trainees, they're not likely to write better schemes of work, better lesson plans themselves than what the experts at the National Centre of Computing Education have already produced. I'll drill in on the detail of one of those units. So let's take the Year 8 programming unit there. I love this concept map which the team at the NCCE have put together for what one unit of programming looks like. What are the individual constructs that pupils should learn at the age of 12 or 13 when it comes to learning to program in Python? How are these individual constructs dependent on others? Is there a logical sequence to that? And doing that first before writing the curriculum materials seems a really smart move on their part. This is what one of their slides looks like. So they've produced the whole PowerPoint presentation to drive the lesson. They've produced assessment materials and the lesson plans. I think this is just such a gift to the profession, and about time too, I would say. And then when we went into the whole lockdown thing of sending our pupils home from school at very, very short notice for our third lockdown, the National Centre working alongside our Oak National Academy to produce the video versions of those lessons. So rather than delivering face-to-face training, many of the NCCE team just recorded lessons as if to the pupils. And so a lot of schools that didn't want to do the online teaching themselves, making very good use of these really high-quality computing lessons together with that video recorded content there. At A-level, the 18-plus qualification, we've tried to address this too. So we have 3,000 teachers enrolled, 54,000 students enrolled in this 18-plus elective qualification support program put together by computer science academics at Cambridge University there. 2.9 million responses to questions on that site, such as that object-orientated one I showed you earlier. And now the Isaac team are producing resources for our 16-plus qualification, which I hope will drive up uptake for that as well. Other resources too, so the BBC, our national broadcaster, decided to get involved with this. What could the BBC do that nobody else had done? Well, producing really lovely TV programs to accompany things. But they remembered the days back in the 1980s when I was learning to program, of the BBC Micro, which is how me and many of my generation in England learnt to program, together with high-quality BBC programs. And they said, what would a BBC Micro look like now? And produce this tiny wee circuit board computer. You're used to, I don't know, multi-million pixel displays on your mobile phone. This has a 25-pixel display. It has 2 buttons on it. Okay, it's got an accelerometer on there as well. So, you can do lots of things at a very low level. This idea of giving pupils this notional machine, a model of how computation works, is so much easier on a simple computer like this than it is on a sophisticated piece of technology like this. And notice again the block-based language. You don't need to learn syntax in order to be able to write a very simple dice rolling program on the microbit there. And of course, famously, the Raspberry Pi, which about 10 years ago now that the first Raspberry Pis came out on the 29th of February, and we have that model there of, again, a simple computer that you have some more chance of being able to understand. Raspberry Pi was originally intended for schools to allow pupils access to the operating system. Typically, school computers are so locked down you can only use the programs that have been approved by the network technician, the network manager. For the Raspberry Pi, it doesn't matter if you hack the thing. You just swap out the SD card, put a new SD card there. So this idea of giving pupils access to the lower level of the operating system stack. And still, today, the Computer Science Laboratory at Cambridge University saying for those wanting to apply for the degree course there, don't worry about the A-level qualification, get a Raspberry Pi. Learn Linux on the Raspberry Pi, make something interesting, and come and talk about that when it comes to the interview. I'll finally move on to what the incentives have been, and want to talk really about the measures of our success. So one of the issues has been persuading those who've just got a degree in computer science And there are a lot of very lucrative career pathways that open up to somebody who's just got a good degree in computer science to train to become a school teacher. Why would you do that? Well, one of the incentives is quite a generous tax-free bursary administered by the British Scholarship, administered by the British Computer Society with funding from industry to make this happen. So train to become a computer science teacher, and there's a golden hello there, which makes it perhaps that not quite such a pay drop from those very lucrative jobs out in the software industry. And some of my best students at Roehampton have been those who've been awarded the BCS scholarship, and I hope will stay in the profession for some time. We still don't hit the recruitment target for almost every year since we started this journey, 2013 up to 2019. We were about 2/3 of the model of how many new computer science teachers we needed year on year. 2020, 2021, we actually hit the target slightly more than the number we needed, in fact. So that was seen as a mark of success. That said, this was during the whole of the sort of lockdowns, the pandemic, lots of employment being closed off, the loss of opportunities. So I don't know whether it was I could still become a teacher, or whether it was folks who'd had such a lovely time teaching their own children at home that they decided they wanted to train as a teacher themselves. So 2020, 2021, we did well. This current cohort, again, we're at about 2/3 of the target that the model says we need. And the fact that the model has gone up suggests there is a retention issue for computer science teachers. We need more teachers now because some have left the profession during this lockdown period. The numbers taking the qualification have kind of leveled off. So the red line here is the new computer science qualification at 16 plus. And you'll see that's broadly stable around the sort of 77, 80,000 level for the last 3 years. This seems about the right number as things stand. To get to a higher level, I think it would come back to rewriting that qualification, making it more broader, making it an easier qualification in which pupils could do well, taking out some of the dry, dull content like Boolean logic and binary arithmetic, and focusing it much more on the practical applications of computing, on digital media work, on human-computer interaction. There are things that we could do, but we have what we have in terms of the qualification there. One of the things that really worries me is the sort of school that offer this qualification. It is, as I say, an elective qualification. It's there as a choice. And it turns out that schools that are in very affluent catchment areas, very nice middle-class areas, parents who've got a degree themselves, a good salary, you're more likely to find schools in those areas offering the qualification than schools in the poorer areas of England. England is a very divided society economically, and so it doesn't seem fair that your ability to take a qualification in computer science seems to be determined, at least in part, by the affluence of the area that you come from. There's more we can do about this. So when you look at the gender divide in computing, computing is almost the worst subject. 80% of those who take that 16 plus elective qualification are boys. Only 20% who take it are girls. Why is that? What can we do? My argument is change the nature of the qualification there, but there may be more to it than that. Again, positive female role models in the teaching profession is part of it. Also, a big part of it is that we think girls see this as a very difficult qualification, although the grades that our female pupils get are very high compared to the boys. There's still a perception that this is a hard, dry, dull subject from time to time. At A-level, the overall numbers continue to increase, so the 18-plus qualification has seen a steady year-on-year rise as more students are electing to take this harder qualification at 18+. The gender divide is even worse, though, when it comes to A-level, with, I don't know, that's about 14, 15% of the cohort of female students, and we really do need to address that, I think. One of the ways we're trying to do this is an accreditation for schools, so again through the National Centre for Computing Education, not just teachers getting certificates now, but schools being awarded as a certificate as a good centre for computing education. This is very, very new. The first 15 of these certificates have now been awarded, many, many more to come. I'm very nearly at my last slide. The last point I really want to make is that this is a vision for computing for all. This isn't just about those who come from the nice middle-class homes or just those who have parents who have jobs in the industry. It's certainly not just for the boys. By putting this onto the national curriculum, we're saying everybody should learn at least some of this subject. This is so important. Yes, for some future employment, but much more about your understanding of the way the world works, of being able to solve problems, and an appreciation of how the digital technology on which we've come to rely has been made. So this is an entitlement for all, is the model of the English approach there. So yes, my concluding remarks, at last, just writing the curriculum content wasn't enough. You have to do more than just write a specification for this. The lesson that Oates gave us back in 2010 of plan for coherence, of address all 6 of those dimensions, I think is really important one for people to learn. The capacity of the professional development, initial teacher training are really, really important, as are the resources that teachers can use for this. And some thought needs to be given to how to teach this subject well. I love this pragmatic approach of let's try this, let's see what works. But we've been doing this in schools since 1980 with Papert. We've been doing this in universities for even longer than that. Let's draw on the lessons learned in those perhaps different contexts to come up with a good pedagogic approach to teaching computing in schools so that all have a good chance of succeeding. I should also say, give thought to the transition. We did this on the 1st of September 2014. Everybody started all at once on the new curriculum. That doesn't really make sense because the stuff which you're wanting to teach to 14-year-olds assumes that they've already learned, 7, 8 years of computing before they get there. So phase it in would be my advice to anybody doing this. And yeah, have in mind this vision of this is an entitlement for all, not just for some. Thank you so much for listening to me at the end of what I think has been a really interesting morning. Thank you very much for your patience. Thank you. I'm happy to take questions if we have time. One at the front.
Thank you, Miles, for your presentation. I have one question. Everything that you told about is on England or at the UK. Is there any other experiences beyond England in the UK, in other in the
So education is one of the things which has devolved to the 4 nations. So England is very much the dominant country within the United Kingdom. Scotland, Wales, Northern Ireland are relatively small populations. Each has their own education system, and they're very, very proud of the distinctive features of their education system. That said, all 3 of the other countries have taken the lead from England by implementing some aspects of computing education as part of their own national curricula, which they have control over. There's a really good 4 Nations report from the British Computer Society. Happy to send you the link to that. Happy to send anybody else the link to that, which draws some of the comparisons between the English story, which is all I've been talking about today, and what's happening in the other 3 UK countries. So by putting that pizza slide up, I've obviously whetted people's appetite. Thank you once again for listening to me this morning and for having me here.